Thank you for the introduction. My name is Gotoda from Japan. I have been, during the last few years, my main focus in 3D displays is on multilayer displays. And today, I'm going to talk about the extension of multilayer displays. So some of you have been already familiar with multilayer displays, but just to refresh your memory, multilayer display is an stereoscopic display constructed by stacking multiple pairs of panels, multiple panels on top of a light source, and images are simultaneously shown on these panels, and viewers will observe the superimposition of these images. And in my talk, I'm going to talk about present an extension of multilayer displays where a pair of lenticular sheets are attached to both sides of each panel. And I'm going to talk about results of computer simulation, showing that some artifacts or inconsistencies that are present in conventional multilayer displays can be resolved by that extension. So here is the outline of my talk. So I'll give a very quick introduction to multilayer displays and turning our attention to some peculiar phenomena that we sometimes encounter with multilayer displays. I then propose extension of multilayer displays and show some simulation results and conclude my talk. So this is a very quick introduction to multilayer displays. And well, as I mentioned, that multilayer displays is displays constructed by stacking multiple panels. And these are structurally similar to volumetric displays, but these multilayer displays are expensive from a computational viewpoint. This is because images to be shown on each layer of displays must be it is not very simple to derive the images to be shown on each layer. So there's a vast amount of computation to determine what kind of images to be shown on each layer. Multiplayer displays are capable of reproducing the light field, but the reproduction of the light field is only approximately, meaning that some blur or artifacts is often introduced in the reproduction. So here's an example of layered images and views derived from these layer images. So in this example, 4 images exist in the display. And if we look at these images from various directions, we get these views. And these layer images are derived so that a correct light field will be reproduced. So in this slide, we compare the correct views against generated views. And basically, these two, there are of course differences between correct views and generated views. As you may notice that there are vast area of black regions, where a vast area of black regions, which is not present in correct views. But apart from that, these images are basically the same. But if we look at a closer look on the generated views, there are artifacts. For example, in this example, the object is broken into two pieces. And in the right image, you see that the object here is smashing into another object, which does not take place in the real world. Here's another example of peculiar phenomena where the correct view and generated view are quite different. And in this example, objects here, this is actually the chessboard with pawns. And in the generated views, pawns are very transparent or ghosty. So the background, the chessboard is visible through these pawns, which is not good, which is not very good. So in order to address these problems, we are going. I'm considering an extension of multi-layer displays. But just to summarize what we have observed, that images from multi-layer displays are poor at oblique angles. It also happens that object too near or too far tends to be obscured. And these two phenomena are somewhat related to viewing angle or viewing range. So I start to consider that how about stacking view-dependent pixels, panels consist of view-dependent pixels rather than normal view-independent pixels like LCD panels. So my idea is very simple. So stacking view-dependent pixels like this one. So there are two possibilities, left configuration and right configuration. On the left, we see that each panel is attached to to each panel, lenticular sheet is attached to one side of the panel. But this configuration does not make sense because the micro lens, lenticular lens serves functions as a diffuser of light. Another configuration is this one. So to each panel, we attach a lenticular lens from one side and also on the other side. If we configure these lenticular lens accordingly, we can get a situation that the parallel rays of light will arrive at this, converge at this point, and leaves in these two directions. So a single bundle of parallel rays will converge at this point and diverge, goes out in two directions. So in the right example, there's no light spreading. So I adopted this configuration and see how this works. So the problem, there's a problem with the second configuration that is ray splitting. So so as I mentioned, that the parallel rays of light will come here and split into two parts. But this splitting will often result in two-folded images like this one. So here is a box, and here is a ghosty box around here. So in order to avoid such ray splitting, I built a small shutters on top of the panels. And since we are dealing with LCD panels, this is simply done by inserting a polarizer between lenticular sheet and liquid crystal layer. So in this example, a single parallel ray of rays of light will come here and split into two parts. One is going left and one is going right. And so we control left going right and right, we divide left going right and right going right using this polarizer and liquid crystal panels. So that at one time we deal with only left going right, at another time instance we deal with only right going right. So I'm going to show some results of computer simulation. So on the left, there's an image produced by conventional multilayer display. And on the right, the image is reproduced by multilayer display attached to, augmented by lenticular sheets. And as you see that, image quality of this image is better than this one. But well, as I mentioned that there's a problem of object splitting into two parts, which is not visible in the extended in the image produced by the extension of the multilayer display. Another example is here. In this example, object here is smashing into another object, and such kind of smashing is also visible in the extended version, but the degree of smashing is a bit smaller. And there's a clear distinction between these two images. Left one is produced by the multilayer display, conventional architecture, and the second one is the one produced by the extension. And well, as you see that objects are more clearly visible, there's no occlusion, object's occlusion is properly handled in this example. And this object is now visible here, not visible in this image. So in general, image quality in some portions multilayer display is superior to the extended multilayer display, but some peculiar phenomena can be avoided by the extension. Well, so, but unfortunately, the current research status is that I have done only computer simulation only. So I tried several times to implement this one on a physical display, but I have not been so successful. This is probably due to poor lens alignment, I think so. So theoretically, it seems to work, but practically, I have not observed the right scene, verified the real images. And also, I didn't mention that, but these things, but I have been dealing with only horizontal parallax only displays here, but multilayer displays can provide vertical parallax also. So maybe I have not verified yet, but maybe replacing lenticular sheets by micro-lens arrays may work, but not verified yet. So in conclusion, I presented an extension of multi-layer display where each panel is sandwiched between a pair of lenticular sheets. And I did simulation-based studies on this structure and showed that some types of artifacts are resolved by the extension, but the detailed analysis of the extension and as well as a real physical implementation of the prototype is left as a task of the future research. Okay, that's the end of my talk. Thank you for your attention and time.
Thank you.